paper adds the idea of the EPR criterion of reality, according to which the ability to predict with probability 1 the outcome of a measurement upon B implies the existence of an element of reality between B or within B.
So what do you think so far?
What's there to think? I mean,
Do you understand what is at stake?
I was just some physicists debating with each other about the assumption of reality, right? About locality.
Well, both reality and locality. What is reality? What does that mean?
You already asked me that.
So what?
You already asked me, and I answered
So what if I asked you? What's the definition of
you.
realism?
Just that there's a world outside of your perception.
I would say realism is the question: is the moon there when we're not observing it? Does a particle have a state? Does an electron have a definite state before we measure it? Therefore, is the moon there when we're not looking at it? Is the cat in the box dead and alive?
No.
Or is it dead or alive? So Bell said it's dead and alive. The cat in itself is in a superposition of every possible state as long as we don't measure it.
And then your philosophy depends on your.
No, Bell proved that the
Well, that's
cat.
according to Bell and the people who say that he proved it, right? Like, I mean, that's
Well, so
according to physicists.
you have to disprove Bell.
I don't have to do anything.
Yes, you do.
Come on, if I had to disprove everybody who ever proved anything, I mean, that would take forever. Like, I would just.
But in this case, he proved there is no reality. How do you
Faith.
go
That is
on?
faith.
How can you continue after that?
I have no idea, dude.
So you have to stop and think. You have to answer the question. How do you disprove Bell?
No, no
What?
one knows how to disprove that. I mean, it's a complicated question.
No, it's not
Yes.
complicated at all. It's actually very simple. What's Bell's proof that the moon is not there? What's his proof? What's the proof? Are you alive?
I am alive. I was just doing something. I was busy.
What's Bell's
But I
proof?
mean, what's Bell's proof?
Hmm.
He has his his ideas there, where he's presenting his ideas and he's like, "This is proof," and people go, "Wow, that's the proof," and that's how it works. I mean, that's
And they gave him a Nobel Prize.
yeah, they did, yeah,
I mean, they didn't give him. They gave the people who
did the
proved.
experiments for
Yeah.
Nobel Prize.
What's the
Yeah,
experiment? Tell me the experiment.
so And they got people in rooms with particles. I don't know. I haven't read the experiments yet.
They put a bunch of people and particles in rooms. That's the
Yeah,
experiment.
it is. It is, and it proved
and, they,
non-locality.
and they prove that's it. That's the proof. A bunch
Yeah,
of people
they
and
proved.
particle. Well, the proof involves a bunch of people and particles. That's for sure. Hmm.
That's it. That is it. There you go.
Hmm. So what
Yeah.
Bell
But there are
did.
always these physicists who are obsessed with people in rooms with particles. That's their whole job. Is just like going around going, oh, there's some particles over here. Let's have a look at these. And
Right.
then they turn them around and they spin them and they watch them decay. Poor
Exactly.
particles are like, you spin me round like a record, baby, round, 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 round. You know,
Exactly. Hmm.
they're probably
Anyway,
even playing music while they're spinning the particles. You don't even know
so
what these guys are up to.
Bell, he said, let's assume Einstein is correct. If Einstein
About
is
what?
so Einstein
About
said
the assumption of realism or about
Einstein
locality?
said a particle has a definite state before we measure it.
Okay. I mean, that's fine. I mean, you can assume that, right? You
Okay.
can assume that if you want.
Okay. So
Do you
he
have a proof that proves the?
so so Bell said, let's assume Einstein is right. If Einstein is right, then this has certain ramifications,
Yes, it does.
which are
There's all the ramifications.
which are incompatible with quantum mechanics. It's either right. Quantum mechanics said a particle cannot have a definite state until we measure it. So there's a
Right.
dichotomy. It's either
Okay.
Einstein or Bohr.
Okay.
It's either realism or non-realism. So Einstein believed in realism. Bohr believed in quantum mechanics and anti-realism, non-realism.
Yeah.
Bohr said
Realist versus anti-realist. Is anti-realist up to no good again? You know.
exactly. So Bell said, let's prove Einstein is right. But if Einstein is right, then quantum mechanics is wrong. But everybody knows quantum mechanics is right. Well, let's go through this test just to be extra sure. And lo and
Right.
behold, they went through all the tests and they closed all the loopholes. And the conclusion
Mm-hmm.
is Einstein is wrong. Therefore, a
Damn, bro.
particle.
Rest in peace.
So,
Massive L to Einstein right there.
right. So the conclusion is therefore a particle cannot have a definite state before we measure it. Therefore, the moon cannot be there when we're not looking.
You think, how did it get there in the first place? Who was the first person to observe the moon, and why was it created when they observed it? Like, why, you know,
No, but when you look
I wonder
away,
what's happening preceding the observation.
no, but when you look,
But I mean, you know, the first, yeah, yeah, go on, yeah,
when you look away from the moon, it goes back into superposition. Superposition is the state in which a particle is in every possible state that it can be. So,
uh-huh.
for example, a cat in a box that you're not observing that could be dead, therefore it's both dead and alive until you open the box. When you open the
Right,
box, the universe has to decide if the cat is dead or alive. Until now, the universe
right,
could not decide because no one observed it. So until that
right.
time, the cat is in every possible state. It's dead, it's alive, it's dying,
That
it's
cat's busy, bro. That big cat is busy. He's multitasking. He's like
that's
getting
that's
shit done
exa-
right there.
that's exactly
One busy cat.
the idea of the multi-world. The many world interpretation comes out of this, exactly out of this. But since the cat must be in every possible configuration,
Mhm.
therefore there is an infinite number of universes. Every time a particle can be in multiple states, the universe splits into every possible configuration. And this is true for every elementary particle in the universe. So there is an
Wow.
incredible number of universes being created all the
Mhm.
time.
Damn, bro.
And this is Sean
There's a
Carroll's.
universe where I'm telling you about Bell's inequality, and I'm telling you that,
There's a
and you're
universe.
listening to me say that.
There is a universe in which Miss Universe is under your table right now.
Damn, bro. I hope this is. I'm gonna check if this is this universe. Okay, I'm gonna go check.
Oh my
God
god!
damn it! The fucking superposition RNG random number
Wrong
generator got me
universe.
again. I'm gonna look again because maybe the position changed when I wasn't looking. Oh fuck! This stuff. There's only fucking bottles of water under there. Oh, the only information I'm getting looking under the table here is I need to clean. This sucks, bro.
So Sean Carroll, probably the greatest physicist alive, he
Hmm.
believes in the many worlds interpretation of quantum mechanics.
Okay.
Uh,
And can
and
we use this to our advantage to get like Miss Universe to appear? Like I'm not,
definitely,
it's like,
that's the only
and
way.
then
Apparently, there is no
we
other.
get quantumly entangled with Miss Universe,
Oh.
and we could be in all kinds of positions.
Anyway, so yeah, so
Oh my god! Someone should do this. Someone should be like some baller physicist, savage, should be like, "There's a universe where I'm banging your mom."
anyway, so getting back to the conversation. So I mean,
Oh,
obviously,
God.
this is utter nonsense, but apparently, no one has been able to prove that it's nonsense.
Uh-huh.
So it's up to you.
Yeah, exactly. Subjective. It's all um to do with the mind, through observation.
So
My question is, I wonder what it is from their point of view about observing that makes the thing happen. You know,
that's
like
called
what's the mechanism?
that's actually called the measurement problem. Uh, um, obviously, I
I love
don't.
the way that they proved it with it like another problem, but yeah, go
No, obviously, I don't
on.
care. I mean, their philosophy is completely ridiculous, but they claimed that they have the proof. So, can you
Hmm.
disprove Bell? Where is the
Well, I mean,
mistake?
anybody can claim to have the proof. I got the proof under my table. It's
No.
under my table right now with Miss Universe. Okay, that is where the proof is.
So, so I found it's a simple logical fallacy.
Hmm. But what people consider a logical fallacy is subjective. So it's logical fallacies are non-local. Okay? They're only fallacious when they're being observed.
Anyway, so you have. So let's go through the steps. So let me
Yeah,
throw away my gum because now we're getting serious.
we're getting serious. You're here to chew gum and kick ass, and you just finished your gums. Yeah.
I'm fresh out of bubble gum.
Hmm.
All
Wonder
right,
what day it
so
is. Is it Saturday, Sunday, Friday? It is Saturday,
it
right?
is Saturday.
Somebody messaged me. What is messaging? I'm just a girl.
I'm just a girl.
I was just seeing the sun too.
Nevertheless, all right, let's continue. All right, so what is the logical fallacy that everyone makes, that Bell made? What's the logical fallacy? What is the logical fallacy? Name that
You said it
fallacy.
was a false. You said it was a false dichotomy. I think.
Good, very good. So what's the false dichotomy? Okay, let's go through the
That
proof.
between.
Mhm.
Sorry, go on. Yeah, yeah. No, you go. You want to go through
All
the
right,
proof?
so let's go through the steps again. So there's
Okay.
two camps. There is quantum
Yeah.
mechanics and there is
And there's
Einstein.
hidden variables. Is that right?
So every word you're saying now is going to trap you. So you have to be careful.
Yes.
So there's two camps, quantum mechanics and Einstein.
According to who?
According to
According to Bell.
according to everyone.
According to everyone. Okay.
And what do you think
What do we think about what?
about this
But
fact?
I mean, there could be two camps. I mean,
There could be
they
two
can say there's two
camps.
camps if they want. I mean, there could be.
Well, in order for this proof to conclude, it's built on the assumption that there is only two camps.
Right.
That's wrong. That's the only mistake. You don't need any other mistake. That's it. That's where the proof is wrong. That's it. It's
Okay.
very simple. So, but okay, that's the title.
You know what to say when you assume. You know, to say you make an ass out of you and me. Currently.
All right.
You would say.
But Bell said there's two camps. Everyone agrees with Bell that there's two camps. There's the camp that a particle has a definite state, that's Einstein, and there's a camp, Bohr, that says a particle does not have a definite state. Okay, so far so good. I mean, it's difficult to believe that there is a third camp. There isn't a third camp. Right? It's this cannot be a false dichotomy. It's either a particle has a definite state or it doesn't have a definite state. If it doesn't have a definite state, then it could be in a superposition of all possible states. That makes sense. I mean, it doesn't make any sense, but fine. Logically, there's two
We
camps.
don't have like the quasi realists as coming in as
Right.
like a third camp or something now.
Right, but okay, it's fine. Einstein believed that a particle has a definite state. One camp believes there is a particle has a definite state before measured, and the other camp says no, it doesn't have a definite state until it is measured. Everyone agrees when it's measured, there's a definite state. Everyone agrees when you open the box, the cat is either dead or alive. When you look at the moon, it's there or it's not there. Everyone agrees. No one says that you ever observe a superposition.
I don't know. There could be zombie cats. You know, there's living dead cats that could come out of the woodwork anytime.
That's true.
It's when you drop your guard. You know, that's when they get you.
I mean, that is
Just
also
because you haven't
true.
observed them, you know.
That's also true. I mean, according to the camp that says that the universe is in a superposition until it's observed, there must be exceptions that the universe just misses us observing it, and we
instead of black
find
swans,
and a black swan, and we see the universe in a
zombie cat.
right. We see a cat smeared both dead and alive. Statistically, it should happen. Anyway, fine, whatever. But okay, fine. Everybody agrees that a smeared existent cat has never been observed. That they're always either dead or alive.
Those bastards.
Yeah.
They're never alive. They're never dead. You know, never both. I don't know why.
Right. So,
There's
all
a little
right.
cat outside my window bullying me right
Oh
now.
my god.
Hanging on my window, and they're like, the cat mafia, man. They're like out to get me, bro.
Anyway,
And preserve the send
So,
help. Send help.
all right. So the two camps are good camps. It looks bulletproof. You're not going to be able to split this thread of hair, this strand of hair. You're not going to split it in two. So there's only two
I don't know. I
camps.
could deploy some next level sophistry here and confuse these guys. I don't know. I bet I could do
Maybe, but
it.
let's assume that these two camps are bulletproof, and it's that
Okay,
you
sure,
can't.
sure.
So it's so far it's a good dichotomy. All right, but now now Bell says, let's assume Einstein is correct, and for this test, and for the next step, and for the next trick, I'm going
Hmm.
to.
And now for something completely different. Yes.
And for the next trick, I'm going to, well, first I'm going to share my entire screen
Wow. The entire
with you.
screen. Jeez.
The
I'm kind
entire
of just
screen.
cutting the log in half right now. Kind of
Now I'm going to look
so
for
proof.
Brian Green Bell's theorem. I'm just a girl. Is this what I'm looking for? Yeah.
I remember I went to a colloquium at Cornell where David Merman was explaining Bell's ideas, and I sort of heard of Bell's ideas. That was, I was a faculty member at that time. I sort of knew about Bell's ideas. I didn't really.
Can you hear it? Can you hear it, Rover?
No, I can't hear it. No, why?
Wait,
Why would I be able to hear it?
I'm sharing my screen. You can't hear it?
No, why would I be able to hear it?
Because I'm sharing it.
It wouldn't I have to click on the thing.
Yeah, you'd have to click on the thing. That's true. I forgot to mention that part, you know. I'm just a
Let me.
girl. Tell
I'm
me.
gonna probably disconnect it soon. Let me see. I don't have any data. I gotta go outside.
All
Where's
right.
your?
You
There's
can't.
your server.
What?
Oh, there's your. There's I found it. Okay, watch stream. Pressing the button, but not this happening. Oh, there we go. Now it's.
Tell me
Oh,
when
there we
you.
go.
Tell me when
I can see
you're.
myself, 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 myself.
All right. So this is David Merman. I mean, on the left is Professor Brian Greene, one of the greatest physicists alive today. On the right is David Merman. And Brian Greene went to Dave Merman. Well, let's hear what he says about this thing.
In the end, as we'll see, a shocking insight, shocking conclusion. But the version of understanding this at a pedagogical level that I will follow, following this example of the particle spins, I learned from this guy over here, David Merman. I was a professor at Cornell in the 1990s. David Merman has been at Cornell for a very long time. I think he may be retired now. And he just had this spectacular knack for drilling down and really finding the heart of an argument. And I remember I went to a colloquium at Cornell where David Merman was explaining Bell's ideas. And I sort of heard of Bell's ideas at that time. I was a faculty member at that time. I sort of knew about Bell's ideas. I didn't really know about Bell's ideas. And after this colloquium of David Merman's, I was just like walking around in kind of state of shock when I finally.
Can you understand what he's saying?
Yeah, what's up?
Okay.
Understood in an intuitive way that I'll explain right now what John Bell was telling us. Okay, so let me show you then how the argument goes in this particular version that David Merman gives us. So here's our detector. We can choose axis 1, axis 2, axis 3, and each of these detectors are in this configuration. And now I should say, when a particle pair is emitted by this particle creation in the center there, it sends the particles out left and right. Now the particles have to have definite spins along all three of the possible axes, according to Albert Einstein. Einstein says, again, particles have definite features. When you measure something that's already there. So if we're measuring the particle spins along axis 1, then the particle better have a definite value to spin along axis 1. And you see it right here. The left particle is spinning up along axis 1, and the right, again, they're completely anti-correlated. That's the nature of this entangled state. But you see particle on the left along the first axis.
What are we seeing? Can you explain to me what he's talking about on the right? What's this thing?
I have no idea what that is. He was just saying something about particles spinning along 3 different axes.
Why
I
is
didn't know what he
there?
was talking about.
So in the beginning,
I just like it looks like there's 3 dildos on the counter. I don't really know.
yeah, we're gonna have to start from the beginning, but it's. Let me try and start from the beginning.
In theoretical and experimental
Why?
physics. I'm not sure.
Because I'm not gonna because he's explaining the notation, and you need to understand the notation. It's gonna go faster if we just let him talk.
Okay, well, I gotta go. I gotta go do some stuff. I'll be back in a bit.
Okay, bye. Anyway. So obviously the false dichotomy, for anyone curious to know, the false dichotomy is that there's three spins. If Einstein said this, then obviously that's the mistake. That's why the Einstein camp is incompatible with quantum mechanics. But here is a version of hidden variables that is compatible and gives the precise, almost precise. I'm still working on getting the precise, but this is very close to the expected results. And it's 50%. This is the 50% that everybody's looking for. But I want to make it. I want to make it better, because right now I'm not getting the 1. This is only 75, and this is 25%. So this needs to go to 0, and this needs to go to 1. So let's fix that. So the problem is, I think it's here. A message from the underworld. Oh. I'm just a girl. One second. Let me check. I'm just a girl. Let me check something very important. Let me check. Checking the hours. Yeah, the store. That's terrible. I'm looking for the hours, for the opening hours. Where do I usually go? Mm-hmm. Okay. All right. Let's get back to this. So what I want to do, probability up should be the weight of a coin. This should be the weight of the coin. The coin should be between 0 and 1. But it should be weighted, right? It's either, but this is some probability of between 0 and 1. And this should be the weight of the coin. Can you create a weighted coin that gives you this probability? Let me see. How do you get help in this thing? Gemini? No? Well, that didn't work. So let's copy here. Can I create a weighted random variable? Yes, you can create a weighted random variable in Python. Here is how you can do it using NumPy. Values, weights. What does that even mean? Can I create a weighted coin in NumPy? Yes, you can create a weighted coin. Generate a random sample from a multinomial distribution. Oh, look at this. Heads is P, tails is 1 minus P. So this is, define the probabilities, the weights. Okay. So NP random multinomial, N, P heads, P tails. Wait a minute, but where is, oh, P, so you say, what is N? The result, convert the result to a binary array. No, I don't want an array. Create a weighted coin. Function can be used to simulate a weighted coin flip. This function generates a random sample from a multinomial distribution. I don't know what a multinomial distribution is, which is a multivariate generalization of the binomial distribution. What's a binomial distribution? Some experiments. So flip. So this is the flip. Return heads if random is less than P, else T. But isn't this what we're doing? We're doing, isn't that what we're doing? Mm. Create a weighted coin in NumPy. Calculate the weighted average of a NumPy array in Python. Coin flip codes. Let's try. Let's see, maybe this guy.
Question for you. Imagine you had an honest coin and you flipped it 9 times and somehow you managed to get 9 heads in a row. What are the odds that the next flip, the 10th flip, will also be heads? My name is Adam Ross Nelson and I'm a data scientist. In the video ahead, I'll have an answer to this question. This channel is for current and aspiring data professionals who are looking to enter
If it's not weighted, then it's 50-50.
and level up in the field. If you think that content will be useful to you, I hope you'll click subscribe and also click the bell button so you'll find out when other videos become available. In this particular video, I'll be demonstrating that even after you flip a coin, an honest fair coin 9 times and somehow miraculously ended up with 9 heads in a row, you still have a 50-50 odd of getting heads again on the 10th flip. Now this is an elementary problem for a lot of data scientists. However, if you're new to the field or you haven't looked at this material in a while, this will be a good refresher. Also, for anyone who's
It's called a uniform distribution. Each flip is independent of the others.
coming over to Python from a new language or not yet familiar with Python, we'll let this be a mini coding tutorial as well. For this demonstration, I'll be using a Google Colab Jupyter Notebook environment. The primary tool we'll use here is NumPy. We'll import NumPy as NP. This is a pretty standard import for the data science workflow. After that, we'll define a function that will make 10 coin flips. Essentially, it'll give us a string 10 characters long of either randomly T or H. We're going to use numpy.random.randint in order to get a number between 0 and 1. We'll say if it was a 1, that was a heads. If it was a 0, that was a tails. This particular function will return, as I've set the parameter, will return 10 flips, a string of 10 flips. Here in the subsequent cell, I'll take that function we just created. I'll use list comprehension to create 10 sets of 10 flips. Now that we have an efficient and convenient way to create any length of sets of 10 flips, let's create 1 million flips of 10. Now that we have a million sets of 10 flips, let's again use list comprehension, this time with a conditional, in order to extract all of the sets where the first 9 flips were all heads. Another aspect of this particular cell is I'm only listing out the first 5 examples. Now that we have a proof of concept in code that works, let's go ahead and store all of the examples where the first 9 flips were all heads in a new variable. Just for curiosity's sake, let's go ahead and see how many occurrences there were. Here we see the result is 1,950. So if you flip a coin 10 times and then you do that a million times, 1,950 or about 2,000 of the sets will be all heads for the first 9 flips. Nearing the end of this demonstration, where in fact I will demonstrate that the odds of getting a head on the 10th flip, even if the first 9 flips were all heads, is 50%. Here, I'm creating an array of 0s and 1s. The 1s will be representative of heads, and the 0s will be representative of tails.
All right, it's not what we're looking for. It's very interesting. It's a good tutorial to learn. Maybe that's what I should do. Let's see this guy.
Hey Fixsters! In this video, I want to show you how to calculate the weighted average of a NumPy array in Python. So most likely you already know the NumPy library for data science, and suppose we have a NumPy array, which is the one-dimensional NumPy array. If you print a NumPy array, we get the 3 values 1 to 3, and now suppose we want to calculate the average. Then we simply call numpy.average.
NumPy array 1, 2, 3. Average
Of this NumPy array, so this is the normal average. So let's
2.
move the output here. Okay, you can see.
Is it 1 plus 2 plus 3? 3, 4, 5, 6 divided by 2 is 3. 6 divided by 3 is 2. So is it 2? Yeah, it says 2.
The average is 2.0 because we calculate 1 plus 2 plus 3 divided by 3. And so in total, we have the average value of 2. 2.0. Average is always a float. But what if you want to calculate a weighted average?
So he says how to calculate the weighted average of a NumPy array.
Which means that, for example, you want to assign 3 times the weight to the first value, 2 times the weight to the second value, and 1 times the weight to the third value. So then you simply define the weights argument, which is a list, and the list has as many values.
I don't know. That's different. I want an unfair coin. Oh, a biased coin is even better. A biased coin in Excel. This is Excel. Ah, this is useless. Accepting Bell's theorem. It's so ridiculous. Jesus Christ. And he is one of the best we have by far. Okay, so what I want, I'd like to, let's get back to this guy. So I want to create a biased coin. Mm-hmm. That's literally what we're doing. Then why is it not between 1? It never reaches 1. How is that possible? Right, because some of the times probability up should be 1. And then it's going to return up. If it's 1, it should not be randomized. Like the weight of the randomness should be reduced. This is so difficult. I cannot think of this. Think how it's working. So it's just a random number between 0 and 1. And this is a number between 0 and 1. When this is 1, when this is perfectly 1, then it doesn't matter what this is. Unless this could also be 1. But I think it cannot. When this is 1, then it's always bigger than any random number, because random is between 0 and 1. Then why is it not, then at 180 it should be exactly 1, and this doesn't look like 1. This is 6, 7, and this is 8, and this is 7.5 or 0.75. Why is it not 1? And the same goes for 0. 0 is never greater than any random number, because this is never 0. This is always bigger than 0. So 0 is always down. So at 0, this is 0. Cosine of 0 is 1. So that's 0. So at 180, this is 90. Cosine of 90 is 0. Then it's 0. Zero is always down. It's never up. But there is a count, and something is wrong with the counting. Probabilities up count plus down count, calculate probabilities. So up count is an array, and up count goes down. These are both arrays. I guess this is the addition of the array. But for example, for 0, but we don't know. Cosine of half the angle. It's up to 360. But let's say up to 180. 180, this is 90, and so the maximum is the cosine of 90, which is 0. Cosine, I gotta go for a minute. I'll be right back. All right. Okay, so when the angle is 0, This is the difference. So this angle might be 0, but this angle is something else. We don't. This could be anything. But since we're only looking at the cases where A returned up, particle A is up. Why is the angle divided by 2? Let me look at my notes. In my notes, I have the original drawing of the logic, which is the same basically as these drawings. I'm just a girl. Same as this. So particle A is up. It could be pointing anywhere towards the upper half of the universe. That means particle B is pointing down. These are the cases we're dealing with. How do we know particle A is pointing up? So we took the difference between the Z angle and this angle. So let's say there's a tiny bit, and we're saying half of this difference, that's going to be what's at play, the cosine of that. Why is it half? Wait, I have a message. Of course, when I leave my computer, I get an important message. All right. So I just want to make sure that particle A is pointing up. There's no point in particle A pointing down and us getting an up measurement. That should never happen. I think that what they're doing is exactly that. I think they're saying that even if it's 180 from 0 is divided by 2, and only then does it stop. I think we should remove this division by half. Let's try removing the division by half. Oh my god. Oh my god. Let's see what happens. Yeah, that doesn't make any sense. Why is it so slow? All right, so this says particle A told us it's up, so now particle B is never, this should be 0. Why? How can we get this to 0? That's the question. Why are we not getting 0? Why are we getting 25% at 0 and 75% at 180? So probability up is up count divided by up over down. So at 0, I mean, this is a major problem because this does not agree with the data. The data says that when we measure along 0, we get exactly 0. So when the angle is 0, notice that There's no reason for the difference to be 0. The difference is some random angle minus 0. It's the random angle. Random, on average, should be 0. But they say it never happens. It never happens and this is not that code. The probability up one second. I mean, if you look at the diagram, we're not reproducing the diagram. We need to follow this diagram. So if A is definitely up, then B must be definitely down. So we need to ask ourselves, if A is up, we need to ask, is A up? The code doesn't reflect. The problem is that this code does not reflect this logic. This logic is that let's see the news. Yeah. Come on, open. What's the news? So Biden, whatever the administration says, Assad is going to fall within a few days. Yeah, I think Biden is actually behind the fall of Assad. I think this Turkey is colluding with the U.S. and possibly with Israel against Assad. Yeah. And it's because Biden doesn't want Trump to take office while Assad is in control. Biden wants to weaken Russia because Biden is afraid that Trump is not going to take a hard stance against Putin. So Biden decided to weaken Putin before Trump moves in. I guess that's my analysis. All right. So when we measure along up and we have some angle, I don't see why we need to divide by 2. This division by 2 doesn't make any sense. The cosine squared has no effect. I mean, certainly it's good that the cosine on both sides gives us a positive number. I don't understand why the division, when we remove division by 2, everything is ruined. I don't understand why. So this is up to 360. Right, because the angle could be 0 or 360. 0 to 90 should give us up, and 0 and 2, what is this? This is 180 plus 90, so it's 270. 270 to 360. So 0 to 90 shouldn't it be multiplied by 2? But what I was thinking is that if it's close to 90 degrees, it should, the probability should be shouldn't it be sine, cosine? No, cosine of 0 is 1. If it's completely aligned, it should be the maximum. How do we ask it? Is it from 0 to 90? Then like if it's 10 degrees or negative 10 degrees, it should be. Why does it take it such a long time to open? My God, come on. So whatever the angle is, we need to first normalize it to this quarter. If it's anywhere else, it should be 0. If it's in this quarter, it should be mapped onto this quarter. And if it's in this quarter, it should be mapped, these two quarters should be mapped to nothing. But at 90 degrees, if you're saying the probability, no, this is good. The probability at 90 degrees goes to 0. Right, that's what cosine means. Cosine means if it's perfectly aligned, it's perfect. But at 90 degrees, cosine of 90 is 0. But then it's going to go here and again give us a positive result, which I don't want. So the question is it between 0 and 90? Is the difference between these guys, between 0 and 90? Is the angle between 0 and 90? I could also ask, is the angle between 0 and 90 or 270 and 360? .270, or let's say 360 and 0, that's the same, but let's say 1 degree and 359. So yeah, we're taking the cosine square, so that gets rid of negative cosine. That's not a problem. I would say the probability up is not, because what is being said right now is if the angle is almost 180, only then the probability goes to 0. What I want to say is that the probability here it's a different model. What I'm offering you is a different model. What they're saying is that if particle A is pointing almost perfectly, just 1 degree off of negative z, then it should still measure as almost 0 up. And I'm saying, so I have a different model. This is my model. Which could be the same. So what I'm saying is if they're perfectly aligned, that's great. As they get closer and closer to 90 degrees, You can't say that it's 0 at 90 degrees, but it's not. At 90 degrees, it's half. My God, this is so confusing. It's really confusing. But, I mean, the fact of the matter is that we're very close. I mean, we have the right shape. We just don't have the right numbers. All I'm saying is that where's the paper? How can we magnify this thing? Anyway, the whole problem is they say that Einstein gives a prediction of a straight line. And what I'm saying is that we can take the straight line and feed it through we can map it to the red line, which agrees with the data. So that for each angle, Einstein gives a certain prediction. Meaning I can feed the red line to the particle and tell the particle for this angle, for 45 degrees, when you feel a 45-degree angle, and you're about to give this value, I mean, at 45 degrees, instead of giving this value, this should be the probability. You should flip a coin. You should flip a biased coin of 15% so that in the long run you get 15%. You know? Mm-hmm. What does the particle know? I mean, the particle knows percentage in that direction. Notice that there's no difference between particle 1 and particle 2. I mean, they don't know. A particle doesn't know that it's 1 or 2. So this is true for particle 1 just as much. Because this is just when we compare notes. When we compare notes, then we notice that if we only look at the ups of particle 1, this is what particle 2 looks like. But you see that it reaches at 180 degrees, it's 100%. This is really confusing. This is really confusing. At 90 degrees, it looks like at 90 it's 50%. So, right, this is 75. This is about 90, yeah. So it's getting that right, but why is it not climbing up to 100 or going down to 0? That's the problem. So at 0, when the angle, this is the measurement angle. So hidden angle, that's our angle. And this is the measurement, the difference between, we take the absolute value, just in case. The measurement might be, we just want the difference between these two guys as an absolute value. This is so strange. So this is just, the angle difference is just a difference. Doesn't matter. Let's say this is 0. So it's this minus 0 or this minus 0. But if it's this, if it's like 350, let's say 359. So this is going to be 359. 359 gives you, but 359 is divided by 2. So 360 divided by 2 is 180. It's going to be basically over here. So if it's 90, it's 45. But what if it's 100? 100, there's no difference. It's always a positive. It's always going to give you a positive. So interestingly enough, this is not the same model. So they say it's not the same model. They're using a different model. They're saying even if it's pointing almost perfectly down, then some of the time it's going to give you up. If it's perfectly down, then it's not. If it's perfectly down, then it's down. But if it's a little bit off, it's already becoming statistical. But that does not explain the data. That does not explain how do they get the blue line? I don't understand. And if you say Bell's theorem, you get all these crazy explanations that I cannot follow. I don't understand anything they say. Let's try Arvin Ash again.
30 years. From 1935 to 1964, this could not be disproven. This is where Irish physicist John Bell comes in. And in 1964, he proposed an experiment that could show whether the local hidden variable theory was correct or incorrect. Now, Bell's equation is remarkably simple, but it's one of the most difficult to understand and simplify. So I'll present.
Remarkably simple, but one of the most difficult to understand. That's good. Always a good thing when somebody tells you something is remarkably simple but difficult to understand. It's just perfect.
A highly simplified idea
That's a great introduction.
of how it works, then also show you the simplified version of the mathematical underpinnings later in this video. Now we're going to play a game, and our opponent is going to be the universe. And the game is guess the color of the checkers pieces. Now I want to give a big shout out to Jim Al-Khalili, who shows a similar simplified illustration in a documentary available on Magellan TV. I encourage you to check it out because it's fascinating. If I guess the color correctly, I win. If I'm incorrect, the universe wins. In the first game, I declare that if the colors match, I win. The universe picks the pieces. Now in play after play, I find that I lose every time. So in the next round,
So if they match, I win. All right, but you let them play with the chips, so they made sure that you lose. All right.
change the rules. This time I declare that if the colors are different, I win. The universe picks
Okay, so if the colors are different,
the
well,
pieces. In play
the universe is going to do whatever it wants. So it's going to match because you said if they don't match.
after play, I find that I lose every time again. So I conclude that perhaps the universe has rigged the game against me. This is what Einstein suspected was happening, that the checkers pieces were rigged. He believed that the
How is this related to Einstein?
colors of the pieces were predetermined, and that this information had been known from the very beginning when the two pieces were together. Niels Bohr's idea, on the other hand, was that the red and black don't even exist until the piece is turned over. So I changed the rules of the game again. This time, I do not tell the universe whether match.
This doesn't make any sense. I mean, how is this related to Bohr and Einstein? This is useless. This is just useless. There's no information. Like, we live in the age of information. Basically, there's no information. It's we're being fooled into thinking that there is information, but there isn't. This is not an explanation. There's no way to ask questions. There's no way to debate. And if you look at the comment section, can move faster than light, hence a black hole. What? I don't know what I'm saying here. So if you look at the comment section, the understanding of this material doesn't really come from one video. It comes from watching a whole bunch of them, listening to all their perspectives, and then slowly merging together a coherent interpretation. It's very exciting. Thank you for producing your videos and adding perspective to this problem. Yeah, that doesn't make any sense. You shouldn't need so many videos. You should need exactly one person to explain it to you. This is impossible, and everybody agrees. I have no idea what he said, but I enjoyed listening to him. And this basically, this is today's age. No one understands anything, but everybody's pretending to understand. The most outstanding thing about this video by Arvin Ash is throwing in the explanation of the mathematics in a way for the layman to understand. No other big media company science show has ventured into this realm, not even the BBC. Congratulations. Anyway, this is far and away the best explanation of Bell's inequality I've ever seen or read. Arvin has truly hit the nail on the head. Not too hot, not too cold, just right. I actually think I understand exactly what Bell's inequality is all about. I actually think I understand. Jesus Christ. This is such a joke. Continually stunned at his ability to take incredibly complex concepts and topics. Anyway, it's all positive. It's so terrific. Oh, you're the best. Everything is the best. So everybody's made to feel like they're dumb. But no one really, you can see from the comments, no one understands. There's no way you can understand. I mean, this doesn't make any sense. Nothing here makes any sense. It's not designed to make any sense.
Matching colors or different colors will win the game until after the universe has already picked the checker pieces.
What is he talking about? The universe, the chips? I don't. This is again some analogy, some simulation.
After revealing the checker pieces, I find that I win 50% of the time and lose 50% of the time. Then my conclusion is that indeed the checker pieces were rigged from the very beginning, because my chances of winning would be 50% if the red and black pieces were already picked by the universe. But if I continue to lose, then I have to conclude that somehow the colors of the checker pieces were not chosen ahead of time. Let's look at how Bell's elegant equation proves my conclusion. To do this, let's look at a universe where local hidden variables are correct. In other words, entangled
What is local hidden variables? What are those words?
Particles have predetermined properties which are complementary to each other at the moment of their creation. Note that this is not an interpretation of quantum mechanics, it's an alternative to quantum mechanics. So in
Notice that he says, I'm going to be spin up. That means they're colluding about their measurement, which doesn't make any sense. How could they collude to give the same measurement? But why do they have to collude to give the same measurement? Why can't they just spin in a certain direction and give some arbitrary and use some equation, some formula to give the answer, some probability function?
In this system, when two entangled particles are produced from a process that conserves linear and angular momentum, we will get two particles that go off in opposite directions, and they will have opposite spins as well as opposite directions. Let's say Alice makes the measurement on particle 1 in her laboratory, and Bob makes the measurement on particle 2 in his laboratory. And
her face is huge. That means she's really tiny. She's like 5 foot.
Let's say the two labs are very far apart and are not in communication with each other. If Alice measures the particle spin in the z direction as positive, Bob will measure the spin as negative in the z direction. If they measure the spin in the x direction, which is orthogonal to the z direction, or 90 degrees apart, the same type of complementary opposite spins will be measured. Because as I said earlier, angular momentum is always conserved. What Bell's inequality does...
It's not enough to say that angular momentum is conserved. That's not enough. The fact that you measure in a single in a certain direction, that has nothing to do with the spin. The spin could be in any direction, and there's a probability. This doesn't make any sense. This is so tiring. This is so tiring. Nothing is really explained. What about this guy?
Hello. Today I'm going to take up the challenge of a question that was put on one of my videos and tell you about the Einstein-Podolsky-Rosen paradox, sometimes shortened as the EPR paradox. Now, I'm going to keep this very simple and very basic, consistent with the theme of these videos, to explain things in simple terms. So if you are an expert in this, look away now. It's not actually an issue that I'm particularly well schooled in, but I should do my best to explain it in simple terms. There will be no mathematics. The Einstein
he never gives such a preamble, such an introduction. Why would he give such a weird introduction? I'm not an expert. Why would you say that?
Podolsky-Rosen paper was written in about 1935 and 1936, written by Albert Einstein, Boris Podolsky, and Nathan Rosen. And essentially, they were challenging whether quantum mechanics had got it right. At the time, quantum mechanics was about 10 years old. I suppose you could say that the originator of quantum mechanics was de Broglie, who had postulated that particles, like electrons, could also be regarded as waves, and that they would have a wavelength given by lambda equal to Planck's constant h, divided by the momentum, which for an electron would be its mass, multiplied by its velocity. And that he postulated in 1924. It was a radical suggestion because it made the notion that particles, which had always been thought of as matter, could somehow be thought of as waves. And it was Davison and Germer who subsequently showed that you could get diffraction patterns from electrons, and you can only get diffraction patterns from waves. Schrödinger picked up this idea in 1925 and developed the famous Schrödinger wave equation, and you can see lots of information on that in my other videos. The Schrödinger wave equation and all the theory that was developed from quantum mechanics was demonstrated to be a correct analysis simply by looking at the spectral lines of hydrogen, where those lines precisely agree with the electron transitions within an atom. In 1927, just 2 or 3 years later, Heisenberg came along with his famous uncertainty principle, which is usually written as delta x, delta p is greater than or equal to h bar.
Which is also under the assumption that elementary particles are waves. This is a Fourier transformation.
Over 2. What this essentially means is that within quantum mechanics terms, in subatomic terms, there are certain quantities that you can't measure both at the same time. In this case, it's position and momentum. You cannot measure the position and the momentum of an electron at precisely the same time. If you measure one precisely, the other is undetermined. And that is also the case, for example, if you take the spin of a subatomic particle, let's consider an electron, that will have a spin which would be in any direction, but the component of that spin in, say, let's call this the y direction, the component of that spin will either be up or it will be down. Those are the only 2 options. And the component of the spin in, let's call this the x direction, will either be that way or that way. Those are the only 2 options for the components. Now, what Heisenberg's uncertainty principle says, you cannot both measure the y component and the x component at the same time. If you measure one precisely, the other is completely unknown. The concepts of quantum mechanics were developed in a number of places, but in particular in Copenhagen, where Niels Bohr and a number of colleagues were working to develop the theories. And we get what's often called the Copenhagen interpretation of quantum mechanics, which essentially says that in the quantum mechanical world, things are uncertain and unpredictable until you measure them. Particles have a wave function. Now, it's important to make this clear that we are not saying that lots of electrons become a wave.
That he's mixing up superposition with uncertainty. Superposition and uncertainty are not the same thing. The uncertainty principle, and okay, that's fine. That's the result of waves, because it's a wave, because a particle is really a wave, and when if it's described by a wave, then because of the Fourier transformation, you get the limit, the Heisenberg uncertainty. That has nothing to do with superposition.
Wave, we are saying that every individual electron is itself described by a wave function. And it was Max Born, who has the honor of also being the grandfather of Olivia Newton-John, who made the postulation that if you take the wave function and square it, or more accurately, if you take the wave function multiplied by its complex conjugate, that was a representation of the probability of finding the particle at that point. So if this is a graph of the wave function against position x, then the wave function squared gives the probability of finding the particle at x. But you have no way of knowing where that particle is. You only know what the probability of it being in a particular place is until you measure it. And when you measure it, if you find the electron is, for example, here, you actually locate it at that point. Then what the Copenhagen interpretation says is the wave function collapses. What they mean by that is you can no longer have a wave function, because the wave function is essentially describing the probability of finding the electron at any of these points. But you know where it is, you just found it, it's here. So there can no longer be a wave function. It collapses into a single point because that's where the electron is. Now, a further consequence of the Copenhagen interpretation was that if you get 2 particles that essentially derive from one common...
Which is weird, because you just told me it's a wave. Now you're telling me it's not a wave. this doesn't make any sense. I mean, things are not making sense. Like the whole thing, the whole explanation is self-contradictory.
source, but they are what is called entangled. That is quantum entanglement. So if, for example, you have, let's say, some energy, and out of that energy you get pair production, let's say you get an electron and a positron produced from energy on the principle of E equals mc squared. You've got energy, you can create matter and mass. Then what the Copenhagen interpretation says is that that electron and that positron will be entangled. This means that the properties of one will influence the properties of another. Let's give an example. We usually say that the electron moves across to the laboratory run by Alice, and the positron moves across to a laboratory run by Bob. And they are each going to measure the electron or the positron spin on the, let's say, the y-axis. You remember that was here. So we're going to measure the coordinate of the electron spin or the positron spin along the y-axis. And remember, that can either be up or down, but there's absolutely no way in quantum mechanical terms of knowing in advance what it's going to be. You can measure it, but you cannot predict it. Now, the point is that if Alice measures the spin of the electron and finds that the spin is up in the y direction, then it must follow, because of entanglement, that the spin of the positron in the y direction will be down. And that has been experimentally verified. The two particles are in some way linked, so that if you find that this is up, then this one will be down. Or if that had happened to be down, that will be up. You've no way of knowing what they will be before you measure them, but as soon as you measure that one, you know what that one will be. And the reason for that from the Copenhagen interpretation is that where you've got one system producing two particles, they do not have an individual wave function. In fact, they have a shared wave function. And what the Copenhagen interpretation says, essentially, that this is a superposition of wave functions. These two particles contribute to one overall wave function. And that's the reason why they are entangled. And that's the reason why you can have this certainty that if one of them is found to have an upspin, the other will have a downspin. Now let's consider exactly the same situation. I'll draw it again.
Exactly when I want him to express this mathematically, he doesn't.
We have something like maybe energy, and it gives rise to an electron and a positron, and it goes to the labs of Alice.
I mean, already now it's not clear how they can always get opposite results. How does that work? Already we need an explanation. This is why I came up with a model, with this model that says that at 90 degrees, it's 50-50. Well, everybody agrees at 90 degrees is 50-50. Right, but my model actually gives the correct data. It produces it should produce the red line. Because if does it? No, it doesn't. Because this is just a measurement direction. The particle 1 measured direction was up, and we found out it's up. That doesn't mean that it's spinning up. It could be spinning in any direction. But we measured it up. This is so confusing. Jesus Christ. It's so confusing, but when you listen to these guys explaining it, it's like it's so obvious. It's so simple. It's so complicated and it's simple. Uh, it's so complicated and it's simple. I mean, already this, and they don't explain it. I mean, can you explain this based on Einstein? Fine, based on what's his name, Bohr. Yeah, based on Bohr, there is faster than light. There's instant communication. Fantastic. That's a great explanation. Thank you so much for that explanation. All right, let's take a break. I gotta take a break. We'll break and we'll be back.